Okay, so we have seen the notion of epsilon steadiness. Now let's take an example of a rational sequence whose terms are these. So the first term is 10 and all the other terms are equal to 0. Now, as far as our vague understanding of convergence goes, that is, we have some idea of what it means for a sequence to converge to something. Okay, it just simply means that the further you go down the sequence, the more the numbers become closer and closer to something. Okay, so if we use that vague idea, one can say that in this sequence the terms are getting closer and closer to 0. In fact, that particular aspect is really very drastic in this sequence. Right after the first term, the other terms become in fact equal to 0. Okay, so according to that vague idea, we can say that this sequence is converging to zero within quotes, because we don't really know what this precisely means. We will know, but for that we have to define the real numbers first. And this is the behavior that has led us to the classification of types of sequences that can be used to define real numbers, which we will see are Cauchy sequences. In fact, we are going towards that definition. But in this endeavor to define Cauchy sequences, we have first of all defined epsilon steadiness. Now let us see how epsilon steadiness, in terms of this sequence, what epsilon steadiness says. This sequence is 10 steady because the distances between any two terms, they are either 0 or 10. The distance between the first term and any other term is 10. So that is less than or equal to 10. And if the distance, if you calculate any other distance, that distance is 0. 0 is less than 10. So this sequence is 10 steady, but is not epsilon steady for any epsilon less than 10. It's because of the presence of distances that are equal to 10 that the sequence will fail to be epsilon steady if we choose epsilon to be less than 10. So we see that our notion of epsilon steadiness fails to capture that convergence behavior of this sequence. So that means we need a more robust notion than epsilon steadiness if we want to capture that behavior, and if we want to use that to define Cauchy sequences. And that's where this next definition comes. So this is like epsilon steadiness but slightly different. This is definition 516. Eventual epsilon steadiness. Let epsilon be a positive rational number and let an be a sequence of rational numbers. We say that this sequence is eventually epsilon steady if there exists a natural number n such that the sequence is epsilon steady. That means this notion of eventual epsilon steadiness works like this. You have a sequence of rational numbers and you have a positive rational number epsilon. We will say that this sequence is eventually epsilon steady if you can find a natural number such that if you start if you consider a new sequence whose terms are starting from this stage, that is whose the index of the sequence is starting from that natural number instead of starting from 0. This n may be equal to 0, may not be equal to 0, that we don't have to bother about that. If this sequence is epsilon steady, then we will say that the original sequence is eventually epsilon steady. In other words, an is eventually epsilon steady if and only if there exists some natural number n such that the distance between the terms an and am is less than or equal to epsilon for all n and m greater than or equal to n. Okay. In fact, here in this equivalent formulation of eventual epsilon steadiness, we have just not written epsilon steadiness. Instead, we have written in detail what epsilon steadiness itself means. It means that the distances between the terms of the sequence of this new sequence are all less than or equal to epsilon. More loosely, if this is your original sequence, the terms go on like this without any end, then eventual epsilon steadiness of the whole sequence means epsilon steadiness of this part. If you neglect this first capital N number of terms, then you are left with a sequence which starts from here, that is this sequence. If this sequence is epsilon steady, then we will say that the original sequence is eventually epsilon steady, and that's why it's called eventual epsilon steadiness. We don't know when it becomes epsilon steady, that is when a tail end of the sequence becomes epsilon steady after the removal of first finitely many terms. When that happens we don't know, but it will happen at some stage. That's why, since it eventually happens, so that's why we get eventual epsilon steadiness for the whole sequence. That's what the concept is. Okay, now let us see an example. This will elaborate this notion. This is example 5.1.7. Now here you consider the sequence. The sequence A1, A2, A3, etc. defined by this formula an equal to 1 by n is not 0.1 steady since the distance between the first two terms is this, which is equal to 0.5, and this is not less than 0.1, this is greater than 0.1, it's not even equal to 0.1. So because of this inequality, the whole sequence fails to be 0.1 steady, but is eventually 0.1 steady. Since the sequence an, where n starts from 10, is 0.1 steady. So for this particular case, that value of capital N can be taken as 10 or any higher value. Okay, you can verify why this happens. Here the sequence will look like, the terms will look like this. And you will be able to convince yourself that the distance between any two such terms is less than or equal to 0.1, and that makes this 0.1 steady, and hence this makes the original sequence eventually 0.1 steady. And what about the sequence with which we started? The sequence (10, 0, 0, etc.) is not epsilon steady for any epsilon less than 10. This we have already seen, but is eventually epsilon steady for every epsilon greater than 0. See, that's the point. That's the advantage of defining this notion of eventual epsilon steadiness. The sequence, okay, the whole sequence fails to be epsilon steady if epsilon is less than 10. That is because of the first term. If you remove the first term, then the sequence becomes the constant sequence where all the terms are equal to 0. In that case, you can see that since all the terms are 0, the distance between any two terms is also equal to 0, and that is always less than epsilon. So for that, any epsilon works here. So the sequence So this you can understand, this is the sequence obtained by removing this 10 first term from the original sequence is epsilon steady for any epsilon greater than 0. So that's why the original sequence is eventually epsilon steady for any such epsilon. Okay. Now, having seen this notion, we are now ready to finally define the notion of a Cauchy sequence, and that goes like this. So that is the next definition. Definition 518. Cauchy sequences, named after the mathematician Augustin Louis Cauchy. Okay, let an, okay, this is not exactly how the definition is given in the text, but it's the same thing, just the language is a bit different. Let this be a sequence of rational numbers. Okay, I think I should refill. We say that an is a an is a Cauchy sequence. If for any rational epsilon greater than 0, the sequence is eventually epsilon steady. So just like we used the notion of epsilon steadiness to define eventual epsilon steadiness, we are now defining a Cauchy sequence using eventual epsilon steadiness. Now if we don't say what I mean, if we don't use this term eventual epsilon steadiness and break everything down to their full detail, then we can write the sequence of the definition of a Cauchy sequence. I can't talk properly because of some reason tonight. We can then write the definition of a Cauchy sequence like this in full detail without using any such notion of epsilon steadiness or eventual epsilon steadiness. That means, in other words, AN is a Cauchy sequence if and only if for every epsilon greater than 0 there exists a natural number capital N such that the distance between AN and AM is less than or equal to epsilon for all indices N and M greater than or equal to N. Okay, now there is a thing that I should perhaps mention at this stage. Note that the definition of a Cauchy sequence as well as the definition of an eventually epsilon steady sequence, the sequences we used, there the indices start from 0. However, you can start the index from any integer. If you do that, if instead of this type of sequence, if you have this, say, where n starts from m is some given integer, then the definition has to be modified slightly. It's because here n starts from 0, that's why we have a natural number n. In this case, for a sequence like this, for every epsilon greater than 0, there will exist an integer n greater than or equal to m such that these conditions are true. That will give us a corresponding definition for a Cauchy sequence where the index starts from any integer. That does not change anything. It keeps the concept same. It's just a different situation, that is a different notation, which you will later realize that these two notations actually are nothing very different. You can in fact write any sequence that's written like this, where the index starts from 0, as a sequence that where the index starts from any other integer. Okay, such things can be done. So the notation is not a problem at all. The sequence is what matters. The notation is just a way of naming the sequence. You can give it one name and then you can call it with some other name. That will not change the thing itself. So this is one thing, and the other thing is a remark that comes after this. And the remark goes like this. Let's first write the thing down and then we will try to understand it. At present, the parameter epsilon is restricted to be a positive rational number. Yes, because we are considering epsilon to be a positive rational number. We cannot take epsilon to be an arbitrary positive real number. Because we don't yet have real numbers. In fact, we are on our way to defining real numbers. Because real numbers haven't been constructed yet. However, when we construct the real numbers, we shall see that the above definition does not change if we require epsilon to be real instead of rational. The thing is that the definition of Cauchy sequence that we have given for a sequence of rational numbers, a similar definition is there for a sequence of real numbers. After we construct the real numbers, we are going to define that thing, a Cauchy sequence of real numbers. There, a question will arise whether you should, there also the definition will have the same form. For epsilon there is an n and so things happen. But the question that will arise is that what should you choose epsilon to be? Should you choose epsilon to be a rational number like this definition that we have now, or should you choose epsilon to be a real number? The fortunate thing is that it does not matter actually. Whether you choose epsilon to be rational or real, you will end up with the same definition. In fact, we are going to prove that, and that's what this remark says. And specifically, we will deal with this issue in proposition 614. More precisely, this can be said. In other words, we will prove that a sequence is eventually epsilon steady for all rational epsilon greater than 0 if and only if it is eventually epsilon steady for all real epsilon greater than 0. So it's not an issue at all. And next we are going to look at an example of a sequence which we discussed before this chapter in the last section of the previous chapter, namely the sequence of rational approximations to the number square root of 2. Since we don't yet know what square root of 2 is actually, so this example is going to be informal. Consider the sequence of rational numbers 1.4, 1.41, 1.414, 1.4142, etc. Okay, we considered this sequence in section 4.4. This sequence is already one steady. You can verify that the distances between any two terms that you can see here in front of you, all of them are less than or equal to 1. In fact, all of them are strictly less than 1. If we remove the first term 1.4, then the sequence, whatever is left, 1.41, 1.414, 4142, this becomes 0.1 steady. So the original sequence is eventually 0.1 steady. If we remove one more term, if we remove this one also, removal of 1.41 gives us which is 0.01 steady. So the more terms we are removing, the smaller the value of epsilon we are able to choose and make the remaining sequence, and that is the sequence formed by the remaining terms, that value of epsilon steady. So the original sequence is eventually 0.01 steady. You can remove this one also and the process goes on. So you can write like this. Continuing in this way, it seems plausible that the original sequence is eventually epsilon steady for every rational epsilon that is positive. It seems plausible, it seems likely. This is not a proof, it just is an observation, a conjecture, and hence is a Cauchy sequence. Now the thing is that we don't really know what this sequence is. Do you know? We have been given only the first 4 terms of the sequence. What should the 5th term be? We have no idea. We are just we see a pattern, no doubt. The thing is that we are adding one more decimal digit to whatever we previously had. Here we have 1.4, then we have 1.41, 1.414, but what digit should be added at the end of the decimal number, that we have no idea of that. So that's why we actually have not been given the sequence at all. This discussion is informal because we don't know or have not been told what the given sequence actually is. So we leave this informal example like this. It just gives us an idea of okay, what is the point of this informal example? We started our discussion back in section 4.4 with this sequence as a sequence of rational approximations to square root of 2. So there we proposed the plan of using such sequences to define irrational numbers and in fact in the end define all real numbers. So our idea started with this sequence, and now after observing some things about such sequences that seem like they are trying to converge to something, we defined our notion of a Cauchy sequence. Then we are just trying to see whether the notion of Cauchy sequence is matching with this one, whether this is a Cauchy sequence, because we will need to use this type of sequences to define square root of 2 and everything else. So here it seems that this sequence should be a Cauchy sequence, but because we lack an actual definition of the sequence, a precise mathematical definition, so we can only guess that yes, it looks like it should be a Cauchy sequence, but we cannot prove it at this moment. However, we are now going to prove that a familiar sequence is in fact a Cauchy sequence, and this proof will be a mathematical proof. It will not be a simple speculation, which is this proposition. Proposition 11. The sequence defined by an equal to 1 by n, that is the sequence of reciprocals of positive natural numbers. That sequence, this sequence is a Cauchy sequence. Let us see how this can be proved. So we need to prove that this sequence is a Cauchy sequence. So we will start by choosing a positive rational number, epsilon. It's understood that epsilon is rational because that's all we have right now, right? We don't have anything else. The system of rational numbers is the biggest system that we have. So that's why epsilon is a rational number that is positive. Okay, now we need to choose a positive integer, and see that's why I raised that point. Originally our definition of Cauchy sequence, there we used this type of sequences. Here however you can see that the index has changed. Now it's starting from 1. So the value of capital N that we will need to show it exists, that N should also be such that it falls within this range where this small n, this index is varying. In other words, this n also has to be greater than or equal to 1. Okay, so now we need to choose one such positive integer n, or we need to show that such an integer n exists, for which the definition of a Cauchy sequence will be satisfied. The conditions there will be satisfied. Now this is a place where we should use one result that we have already come across by proposition 441 from the previous chapter. There exists a positive integer n such that n is greater than 2 divided by epsilon. Now what is it that we have done here? Recall that this is the proposition which told us that if we are given any rational number x, then for that rational number there exists a unique integer n that satisfies these inequalities. That was the beginning of proposition 441. In fact, this unique integer n for that given x has a name. It's called the integer part of x, and we have a symbol for denoting it also in terms of x. This is how we write the integer part of x. And the proposition said something else. In fact, from this part, this second inequality, we got the fact that if we are given any rational number, then we can always find a positive natural number n or a positive integer, same thing, that is greater than x. And this part of the proposition made us conclude that there is no largest rational number. If you choose a rational number, no matter how large it is, you can always find a still larger positive integer, which is also a rational number. So it is this part, this conclusion that we are using here. Now in place of x, here we have 2 divided by epsilon. Why exactly 2 divided by epsilon, that you will understand soon. Okay, so we now have something like this. Then for any integers n and m greater than or equal to n, we have, if n is greater than or equal to capital N, then 1 by n will be less than or equal to 1 by capital N, and 1 by capital N will itself be less than epsilon divided by 2. This last inequality is obtained from this one by taking reciprocals. Since these are both positive, n is positive and 2 by epsilon is also positive, so when you take reciprocal, the inequality will get reversed. So that's what has happened here. We have this, and same for 1 by m also. And hence the distance between an and am, which according to our definition of distance, this is this, which is equal to 1 upon n minus 1 upon m. And you can use the triangle inequality here, which we have already proved in the previous chapter. And the inequality gives us this, and this becomes equal to, since n and m are positive, so this is 1 by n plus 1 by m. Now 1 by n is less than epsilon by 2, and so is 1 by m, so their sum is less than epsilon by 2 plus epsilon by 2. This is equal to epsilon. So we can see that for such a choice of positive integer n, whenever we choose integers n and m greater than or equal to n, then the distance between an and am is less than epsilon. That tells us that this sequence is eventually epsilon steady. But this epsilon is any positive rational number, so that's why the sequence we have been given is a Cauchy sequence. Okay. Thus we can write a little bit more nicely like this. Thus this is strictly less than epsilon. You can, if you want, you can write this sort of inequality also. If you have strict inequality, you can write this, but the converse is not true. This does not imply strict inequality. This may imply equality also. For all integers n and m greater than or equal to n. Hence, an is eventually epsilon steady. Since epsilon is arbitrary, n starts from 1. Here I have written 1, okay. So this is a Cauchy sequence. Now a question may arise. I mean, you may have some questions about this choice n. How did we know that this type of choice has to be made? And this is a place where I should tell you about how analysis is more flexible than algebra. First, let us come to the question of how this choice of n can be made. What you need to do is that you start with the thing that you want. You want this to happen. If you work with this and do reverse calculation, you will end up having this. Now, how can this be made possible? What type of integers n and m can be chosen? Okay, we need this to happen. So, we demand something a little more. We need this to happen. Because you see, if you keep this term in this form, you cannot do anything else. Here you have something inside absolute value. So unless you get rid of that absolute value, you cannot do actual calculation. So you want this to happen. So that means this has to be, since this is already less than or equal to this, so we may require that this be true. Now this being true means this being true, so that means I have to choose small n in such a way that 1 by n is sufficiently small, 1 by m is also sufficiently small, so that their sum is less than epsilon. What can be nicer than requiring that 1 by n be less than epsilon by 2 and 1 by m also be less than epsilon by 2, because then their sum will be less than epsilon by 2 plus epsilon by 2, which is epsilon. So that's how you have come to a position where you can somewhat gauge what n and m should be. Now since n and m should be greater than or equal to n, that's how we choose in the condition for Cauchiness. So you can choose your n itself to be such that 1 by n is less than epsilon by 2. This tells you that n should be greater than 2 by epsilon if you take reciprocal. And because you will be choosing n and m greater than or equal to n, so their reciprocals will be even, both of them will be smaller than or equal to 1 by n. That will get the job done. In the very beginning, it is somewhat difficult to go through the process. I mean, in this particular case, the process works like this. For some other sequence, you may have to do something else, but the more practice you do, the more number of cases you see, the easier and easier it will become. And the other thing I wanted to say here is the difference between algebra and analysis. Since in analysis we are dealing with infinity or infinite processes, a sequence has infinitely many terms, and many other infinite processes are there that you will come across, or in fact you have already come across. Limit of a function, differentiation, integration, all these are, in some sense, they involve processes that go on forever. Okay. Now, since we cannot talk about infinity at once using finite objects, if we use finite objects, for example, here we have used rational numbers, then to talk about infinity, we need to use infinitely many finite objects. So what happens in analysis is that you don't get equality easily. If you just simply you are using ordinary algebra and you are trying to guess something that lies far beyond the capacity of these ordinary algebraic objects, then you encounter inequality, not equality. And because you have inequality, so you have some room for making adjustments. This room is usually not available in algebra. In algebra, the objects are rigid. If you want to guess the order of a set, the number of elements of a set, or for example the order of a group, you have to find the exact number. How many functions of a special type are there, how many say automorphisms are there for a given group, you have to find the exact number. So there the job actually in that sense is much more difficult than analysis. In analysis you are doing approximation, but actually you are not doing approximation, you are working with approximations and you are trying to show that your approximations can be made as good as possible, that is your things can be made as close as possible to something else, and in that process you encountered inequality because of that. I mean, you cannot use the whole thing at once and say that this is equal to something whose behavior is infinity like. Real numbers of course are not equal to infinity, but they are objects that require infinitely many rational numbers for their, in fact, definition. So that's why you use approximation, and you have to show that the approximations can be made as good as anyone wants. That is the idea of limit, and because of that you encounter inequality, and that's why there is room for adjustment, and this makes analysis actually quite interesting. You will do well if you are if you are very good with inequalities. If you can manipulate inequalities very nicely, if you can guess things in your mind that involve forming some sort of inequality, then you can make those approximations and you can do the things in analysis. It takes time, but anyone can do it. So that is the point I wanted to make. Okay, after this we have an important notion, that of boundedness. It will be useful when we talk about sequences, and also later on when we see functions, for them also there is a notion of boundedness. So this is bounded sequences. And the definition goes like this: let m greater than or equal to 0 be a rational number. A finite sequence is said to be bounded by m if these inequalities are true for all I lying between 1 and n. Sequence means sequence of rational numbers. Okay, every time we are not mentioning that. An infinite sequence, here they are starting the index from 1, is said to be bounded by m if the absolute value of every term is less than or equal to m. And we say that a sequence, finite or infinite, is bounded if it is bounded by some non-negative rational number. The definition is straightforward, but there are some things to be said about this definition. Suddenly we are saying finite sequence, and we haven't yet actually defined anything called a finite sequence. Roughly speaking, a finite sequence is just like an infinite sequence. The difference is that in a finite sequence the number of terms is finite, that's all. Not that just like an infinite sequence, which we have been discussing about till now, it's different from a finite set. If you take the set of these objects, these rational numbers, that is one thing, and the sequence is something else. Here also the differences are same. In a set, the order in which we write the elements when we write a set in roster or tabular form, that does not matter. Order does not matter in a set. However, in a finite sequence, order matters. If you interchange any two terms, then the sequence will change. There is a first term, a second term, and so on. And the other thing is that elements can be the same, or terms can be the same in a sequence. That, however, is not the case with a set. In a set, usually we do not repeat an element. So the definition just simply says that if you have a finite sequence or an infinite sequence, and if the absolute values of all the terms of such a sequence are less than or equal to some non-negative rational number, then we say that the sequence is bounded by that rational number, and any such sequence is said to be bounded if it is bounded by some non-negative rational number. Now there is a result immediately. Oh, but before a result, we have an example. Okay, so this example, it shows us sequences. The finite sequence (1 minus 2, 3 minus 4) is bounded by 4 or any higher positive, any higher value of m, that is by either by 4 or by m greater than or equal to 4, a rational number. But the infinite sequence is unbounded. Unbounded means not bounded by proposition 441. That proposition which says that there is no largest rational number. So if you choose any element from here, no, not that thing. If someone supposes that this sequence is bounded, then that means all the terms of this sequence, say the sequence is denoted by this, so that a1 is 1, a2 is minus 2, a3 is minus 3, etc. Then absolute value of an is less than or equal to m for all n greater than or equal to 1. Such a rational number m will be there. But you can see what happens when you take the absolute values of the terms of the sequence. In fact, with a little thought, you can work out a definition for this an. An, when n is 1, then an is 1. Okay, that means when n is 2, an is minus 2, when n is 3, an is 3, So we have to figure out this plus minus. So we at least write n, and along with that we have to write somehow bring the minus for some terms, and for some terms the minus will not be there. So we write like this: n plus 1 times n. Now if you put n equal to 1, then minus 1 square is plus 1, so you have 1. If you put n equal to 2, minus 1 cube is minus 1, times 2 is minus 2, and you can see that you are actually capturing all the terms of the sequence. Now our supposition that this sequence is bounded will give us an inequality like this. Now if you find the absolute value of this, what does it tell us? Minus will not matter and the absolute value will be equal to n. This tells us that all the positive integers are bounded above by a rational number. But you can see that if you consider this rational number m plus 1, then according to proposition 441, we can find a positive integer n that is greater than m plus 1. But at the same time this n should be less than or equal to m, so that means m plus 1 is less than m, which is clearly false. So that's why this sequence cannot be bounded, it is unbounded. The sequence this is a different type of sequence where the terms alternate between 1 and minus 1. If this is bounded in fact by 1 but is not a Cauchy sequence. The reason this is not a Cauchy sequence is that if you choose say epsilon equal to 1 by 2, 1 upon 2, then the sequence fails to be eventually 1 by 2 steady. And that is because no matter how many terms you remove from the beginning of the sequence, whatever you are left with, that is again a sequence that looks like this, where you will always encounter 1 and minus 1. The distance between 1 and minus 1 is this, which is not less than 1 by 2, it is greater than 1 by 2. So this sequence is not eventually 1 by 2 steady, and that's why it is not a Cauchy sequence. Because for a Cauchy sequence we want eventual epsilon steadiness for all epsilon greater than 0. Okay, now we can look at that result that I was talking about. It's the result about boundedness of finite sequences. Finite sequences are always bounded. Infinite sequences are not always bounded, but they are bounded if they are a Cauchy sequence. So let's see the result. This is lemma 5.1.14. Finite sequences are bounded. And what is the the statement is this itself. They have written they have taken the statement and made it the title of the lemma also. Every finite sequence is bounded. And since it's about a finite sequence, we can prove this by induction. Induction is still useful and it will continue to be useful no matter how far you go or how deep you go in mathematics. We apply induction on n. If n is equal to 1, the sequence that has only one term, a1, is definitely bounded, is bounded, in brackets you can write by absolute value of a1 itself, because the absolute value of a1 is less than or equal to the absolute value of a1. In place of m you can think of this number and you are done. Assume that the result is true, or okay, see, this is one of my mistakes. I should not call it a result before proving. Assume that the claim is true for some positive integer n. Consider the finite sequence but before that I have to consider some more ink. Say b1, b2, etc., bn, bn plus 1. By the induction hypothesis, that is this assumption, there exists a rational number m that is non-negative such that this is less than or equal to m for all integers I lying between 1 and n. So what are we doing here? We are using the assumption that any sequence having, any finite sequence having n terms is bounded. So these n terms will be bounded by some rational number. We don't know anything about the last term, but then this is less than or equal to m plus this. For all integers I lying between 1 and n plus 1. Okay, now how is this true? This is true because you see, if your I lies in this range, then absolute value of bi is less than or equal to m. So then automatically, since m itself is less than or equal to m plus this is a non-negative rational number, so adding that to m will make it either equal to m when this is 0 or strictly greater than m when this is positive. Because it's an absolute value, it can either be 0 or positive. So that's why in this range all the absolute values are less than or equal to this rational number. And if I is equal to n plus 1, then we have this on the left hand side. On the right hand side we have m plus this, which is also true. So for the entire sequence, this can be taken as a rational number which bounds the sequence. So that's it, that completes the induction. Oh, but we have one more observation to make. We just have to mention that this is again a non-negative rational number. Since m plus absolute value of bn plus 1 is a non-negative rational number, this is bounded. This completes the induction and completes the proof. And finally, unlike so here what we have seen, every finite sequence is always bounded, but that is not the case with an infinite sequence. An infinite sequence may be unbounded also. We have already seen in example 5.1.13. But if it is a Cauchy sequence, then it is bounded. We have seen one more sequence which is a Cauchy sequence, which is not a Cauchy sequence but it is bounded. Cauchiness implies boundedness, but the converse is not true. Boundedness does not imply Cauchiness. The alternating sequence 1 minus 1 1 minus 1, that is a bounded sequence, but it's not a Cauchy sequence. So finally, this is the lemma. Five 115. With this, the section actually ends. Cauchy sequences are bounded. Here also the name of the lemma and the statement are practically the same. It's like telling someone a short story and using the entire story itself as its title. It looks something like that. I can understand, what else can you write here, but it looks quite weird also. is bounded. And the proof is an exercise, the only exercise at the end of this section. See exercise 511. So let us see exercise 511. Proof lemma 5115. Hint: use the fact that this is eventually one-steady and thus can be split into a finite sequence and a one-steady sequence. Then use lemma 5114 for the finite part. Note that there is nothing special about the number 1 here. Any other positive number would have sufficed, okay? Okay, so let us now try to solve this. So we have been given a Cauchy sequence and this is some hint that is also given along with this. So we start like this: since an is a Cauchy sequence, it is eventually one-steady. So eventually one-steady means what? So there exists a positive integer there exists a positive integer n such that the distance between an and am is less than or equal to 1 for all n and m greater than or equal to n. That's what eventually one steady gives us. Okay, now what can we say from this? This implies that absolute value of an, which can be written like this: absolute value of an minus am plus am. Okay, here you use the triangle inequality to write this as an minus am plus, instead of using m, let us use capital N to make it definite. An plus absolute value of an. And now if I am choosing this n, here we haven't said anything about n. Don't think that this n is this n. We have to say that in this new line. This calculation does not depend on what this small n is. It can be any value. However, if we particularly choose this small n to be greater than or equal to capital N, then by what is true here, this difference, which is actually the distance between an and a capital N, that will be less than or equal to 1. Okay, so you can write like this. You can write one more line. This is equal to plus, this will be less than or equal to 1 plus an for all n greater than or equal to n. Okay, so we have proved that the absolute values of the terms an of the original of the sequence, all the absolute values are less than or equal to this fixed rational number. It is fixed because this capital N is fixed, provided small n is greater than or equal to capital N. Okay, and by lemma 5.1.14, the finite sequence this sequence is bounded by some rational m, we can take it to be greater than 0. Hence, you can see that the absolute value of an is less than or equal to 1 plus absolute value of a capital N plus m for all n greater than or equal to 1. y. If the value of n lies in between 1 and n minus 1, including 1 and n minus 1 also, then since this part of the sequence, you see what the hint suggests, the original sequence looks like this. N minus 1, an plus 1 and so on. Cauchy sequence, the fact that this sequence is Cauchy implies that this part of the sequence is one steady. From this one steadiness, we have proved that in this part, the absolute value of every term is less than or equal to this. In this part means the n is greater than or equal to n. It's either equal to n or greater than n. And in this finite sequence part, this part being a finite sequence is bounded by some rational number which we can conveniently choose to be a positive rational number. So the whole sequence will be bounded by this plus this. If your index an, in this, if your index n lies in this region, then the corresponding absolute value is less than or equal to m. So it's less than or equal to m plus something positive, all the more so. And if your n is greater than or equal to n, then absolute value is less than or equal to this. So that is also less than or equal to this plus n. So now the whole sequence is bounded by 1 plus absolute value of an plus n. So you can write, this part is only for the sake of understanding or saying what the hint means. So the sequence is bounded in brackets we can write by this bound. And that completes the solution, and this completes the section also. So after this we will see something new. New means the next section, where we will see more things about Cauchy sequences, how they can be used to actually define real numbers as formal limits of such sequences. So I end the video here. See you in the next video. This is me, Lucifer, from a mathematical room. Have a nice night.